Our planet has a hidden pulse beating deep within its rocky heart. The ground beneath your feet is not a permanent foundation, but part of a living, breathing system that has been rhythmically expanding and contracting for billions of years. This is the revolutionary theory of living continents, a concept that shatters our static view of Earth's history. By the end of this exploration, you will see our world not as a collection of inert landmasses, but as a single, dynamic organism. What geological clues suggest that entire supercontinents moved with a biological cadence? And how could this ancient rhythm have dictated the very evolution of life? How does it feel to stand on a planet that is truly alive? Our planet's story begins with a fever. In its first few 100 million years, Earth was a world of fire and chaos, a sphere of churning magma steadily losing its heat to the cold of space. This was the Hadean Aeon, a name fittingly drawn from the ancient Greek word for the underworld. But this was not a dead world. It was a world in violent, creative labor. The crust that first formed was thin and unstable, repeatedly shattered and remelted by a relentless hail of asteroids. Heat from within was the planet's primary engine, a thermal inheritance from its violent formation that was vastly greater than what remains today. Geologist Robert Hazen describes this period not as a silent prelude but as a time of frantic planetary construction. The mantle below was so hot that it convected with a frantic, turbulent energy, like a pot of water at a rolling boil. There were no rigid, interlocking plates like we have now. Instead, the young crust was a collection of smaller, more mobile fragments, constantly being created at thin, weak spots, and just as quickly being dragged back down into the molten interior. This was a world in constant motion, a system finding its rhythm. The primordial pulse was not a gentle beat but a frantic, explosive hammering, the essential first strokes of a planetary heart learning how to pump. This vibrant, energetic beginning established the fundamental mechanics that would one day allow entire continents to drift across the globe with a rhythm that almost feels like breathing. This frantic early motion eventually settled into a profound, steady rhythm, a cycle of gathering and separation that has repeated itself for billions of years. Think of it as the planet taking a single, deep, impossibly slow breath. The inhalation is the long, slow drawing together of all the world's land masses. Over hundreds of millions of years, scattered continents are pulled inexorably toward one another, colliding and welding together into a single, colossal supercontinent like Pangaea. This gathering force is driven by subduction zones, where old, dense oceanic plates sink back into the mantle, acting like powerful anchors on the edges of continents and tugging them inward. The planet contracts, pulling its land into a tight, consolidated mass. This is the inhalation, but such a tight gathering cannot last. The vast supercontinent acts like a thick blanket, trapping the Earth's immense internal heat beneath it. Pressure builds, the mantle swells, and the crust above begins to weaken and stretch. Then comes the exhalation. The supercontinent fractures, its pieces pushed apart by upwelling plumes of hot rock, and the creation of new, younger ocean floor along vast, splitting seams called rift valleys. This process of continental dispersal, known as the Wilson cycle, is the planet's release, a great outward breath that scatters the continents once more, opening new oceans between them. This rhythmic pulse of assembly and breakup is the most compelling evidence we have of a living planet, a geological heartbeat so consistent it makes you wonder what powerful, internal engine could possibly keep such perfect time. But this planetary heartbeat was not always steady and predictable. While the cycle of supercontinent assembly and breakup provides a grand rhythm, the tempo itself has changed dramatically over Earth's deep history. The modern world experiences a relatively constant, gradual drift of continents. Yet the ancient Earth, during the vast expanse of time known as the Precambrian era, tells a very different story. The geological record reveals a world of violent fits and starts, where tectonic activity arrived not as a steady flow, but in powerful, catastrophic surges. Imagine finding the fossilized tracks of a giant animal. The footprints are not evenly spaced. Instead, you see a cluster of deep, frantic impressions, then a long, smooth stretch with no marks at all, followed by another chaotic cluster. This is what the ancient rock layers show us. We find bands of stone that testify to periods of incredible violence, with mountains thrust skyward and continents ripped apart in geologically brief explosions of energy. These are separated by immense stretches of time, sometimes hundreds of millions of years, where the rock record is quiet, showing little signs of major tectonic drama. This stop-and-start pattern is what geologists call episodic tectonics. The early Earth's mantle was significantly hotter, and this excess heat did not dissipate evenly. Instead, it built up for eons until it could no longer be contained. Enormous blobs of superheated rock, known as mantle plumes, would detach from the deep mantle and surge upwards. When one of these colossal thermal avalanches hit the underside of the crust, it acted like a blowtorch on a sheet of ice. It wouldn't just nudge continents, it would catastrophically weaken them, triggering a rapid, large-scale rearrangement of the world's geography in a terrifyingly short span of time. This concept, sometimes called surge tectonics or blob tectonics, transforms our breathing planet analogy. It suggests a world with a variable heart rate, one that could rest for 100 million years and then suddenly pound with a ferocious, planet-altering intensity. What could possibly trigger such a dramatic surge after such a long silence? The massive thermal avalanches that shook the early Earth were driven by a planetary engine operating far below our feet. To truly grasp the motion of continents, we must descend into the planet's deep interior, where the mantle functions as a vast, slow-moving circulatory system. This is not a realm of molten lakes but of solid rock, a material so hot and under such immense pressure that it can flow over millions of years, behaving like thick tar or warm candle wax. This creeping, colossal motion is called mantle convection, and it is the primary engine of plate tectonics. The process begins with a relentless heat source, the planet's core, which acts like a furnace. This intense heat warms the base of the mantle, causing the rock there to expand, become less dense, and slowly, inexorably begin to rise. These ascending columns of hot rock can travel for thousands of miles over millions of years until they approach the relatively cool, rigid outer shell of the Earth, the lithosphere. Here, the rising rock spreads out laterally, pushing against the underside of the tectonic plates like a subterranean river flowing beneath a frozen sheet of ice. As this rock spreads, it loses its heat to the cold of space above. It cools down, grows denser, and finally begins to sink back into the deep mantle, completing the cycle. These rising and falling masses create planets spanning conveyor belts of solid rock, and it is these conveyor belts that grip the bottoms of tectonic plates and drag them across the globe. You can see a miniature version of this process by watching a pot of thick soup simmering on a stove. The soup at the bottom of the pot, closest to the heat source, warms up and rises in thin, wispy plumes. When it reaches the cooler surface, it spreads out, releases its heat, and then the now cooler, denser soup sinks down the sides of the pot to be reheated. Our planet's mantle does the very same thing, only the pot is the entire Earth, the soup is solid rock, and a single cycle takes hundreds of millions of years. The efficiency and pattern of this internal circulation are everything. In the hotter ancient Earth, this convection was likely more violent and erratic, leading to the catastrophic surges we see in the rock record. A more stable, modern-style convection supports the steady, rhythmic breathing of the Wilson cycle. This planetary circulatory system, driven by primordial heat, is what gives the continents their mobility, and its faint, enduring pulse is what we must now learn to read in the stones beneath our feet. The rocks beneath our feet hold a secret diary, written not in ink but in magnetism. How can we possibly decode the epic voyages of continents that occurred millions of years before the first humans walked the Earth? The answer lies in a field of science called paleomagnetism, a way of reading a compass frozen in stone. When volcanic rock forms from cooling lava, it is intensely hot, and within that molten mix are tiny particles of magnetic minerals like magnetite. As the rock cools past a specific temperature, known as the Curie point, these mineral grains act like countless microscopic compass needles. They snap into alignment, locking in a permanent record of the Earth's magnetic field at that exact location and moment in time. This magnetic signature captures two crucial pieces of information: the direction to the magnetic pole and the latitude of the rock. It is a fossilized snapshot of where that piece of land was located on the globe. Scientists can extract this ancient data by carefully drilling out core samples from rock layers of known ages. By analyzing the magnetic direction preserved in samples from the same continent, but from different geological eras, they can trace a path across the globe. This path, called an apparent polar wander path, looks like the continent's personal travel log. It doesn't mean the poles themselves were wildly wandering. Rather, it shows how the continent itself has dramatically shifted its position over the eons. The most stunning case study is the incredible journey of the Indian subcontinent. Its polar wander path tells a story of breakneck speed. After splitting from the supercontinent Gondwana, India embarked on a solo race northward, moving at a pace that is geologically blistering, covering thousands of miles to its eventual, shattering collision with Asia that threw up the Himalayan mountains. This is not a theoretical model, it is a reliable data trail etched into the rock. Paleomagnetism provides the hard, physical evidence that allows us to stop imagining continental drift and start mapping it. It is the tool that lets us read the ancient rhythm of the planet's breathing, tracing the inhales that brought land masses together and the exhales that sent them scattering. And with this key in hand, we can now turn to the most ancient and faintest of these magnetic signals, to listen for the very first heartbeat of the living Earth. Locked within the toughest crystals on Earth are whispers from a world we thought was lost. In the remote Jack Hills of Western Australia, scientists have unearthed tiny grains of zircon, minerals so durable they have survived over 4 billion years of planetary chaos. These are not mere specks of dust, they are time capsules, each one a vault containing chemical clues to the planet's infancy. When these zircons first crystallized from cooling magma, they trapped within their robust structures tiny inclusions and distinct isotopic signatures. The most startling revelation is the presence of oxygen isotopes that form only in the presence of liquid water. This single piece of evidence shatters the long-held image of a perpetually molten Hadean hell. It paints a new picture of a world where oceans may have pooled on the surface far earlier than anyone believed, a world already capable of nurturing the essential ingredient for life. Furthermore, the very chemistry of the zircons points to their origin in magma that had interacted with older, evolved continental crust, not just the primitive basaltic rock of a newborn planet. This suggests that patches of stable, continental-type crust were already forming and being recycled in a dynamic tectonic system within the first 500 million years of Earth's existence. These ancient zircons did not form in a stagnant, fire-blasted world. They are the product of a planet that was already breathing, already churning its crust in a slow geological dance. Their incredible survival is a story in itself. For billions of years, these minuscule crystals have been weathered out of their original rocks, transported by rivers, buried under new mountains, and yet they endured, resisting being dragged back into the mantle and melted down. Each zircon grain that we hold today is a miracle of persistence, a direct witness to Earth's first breaths. They stand as silent testimony to a beginning far more complex and far more interesting than a simple ball of fire. If these tiny crystals could talk, what other chapters of our planet's forgotten youth would they reveal? These ancient zircon crystals did not drift alone through time. They were passengers on the most durable rafts our planet has ever built, the Cratons. Cratons are the ancient, unyielding hearts of continents, vast blocks of crust that have resisted the planet's relentless tectonic recycling for over 2 billion years. Think of them as the geological equivalent of a continent's bedrock soul. While the lands around them have been crumpled into mountains, swallowed into trenches, and remade countless times, these Cratons have remained almost perfectly preserved, acting as the stable foundations upon which all younger geological drama has been built. You can see their immense, exposed scales in places like the Canadian Shield, a sprawling expanse of Precambrian rock that forms the core of North America, or the Siberian Craton, the deep time anchor for a vast portion of Asia. What makes these geological elders so incredibly tough? Their secret is a deep, cold, and buoyant root. Unlike younger, more temporary crust, Cratons extend not just upwards but also downwards, with a thick keel of mantle rock that can plunge over 200 kilometers into the Earth's interior. This root is composed of material that is less dense and significantly stronger than the surrounding mantle. It acts like a geological life preserver, making the entire Craton block too buoyant and rigid to be pulled down into a subduction zone. It simply floats on the churning mantle below, an immovable object in a world of irresistible forces. This profound stability makes Cratons more than just survivors. They are our planet's fixed reference points. Their enduring presence provides a steady backdrop against which the frantic travels of other continental fragments can be measured. While the Cratons themselves may drift, they do so with a stately, unshakable grace, their cores remaining internally rigid. The real tectonic action, the violent collisions and dramatic rifting that characterize the breathing Earth, almost always happens at their edges. It is along the volatile margins of these stable hearts that new land is accreted, where mountains are thrust skyward, and where the supercontinent cycle plays out its most dramatic scenes. Winding through the ancient hearts of the Cratons are strange, twisted bands of rock known as Greenstone belts. These are not just random geological formations, they are the actual fossils of the planet's first oceans and its most primordial volcanic landscapes. Picture the deep ocean floor from 3.5 billion years ago, a realm of total darkness broken only by the fiery glow of submarine volcanoes. Lava erupting into the cold, dense water would instantly form bulbous, pillow-shaped mounds, piling up to create vast undersea mountain ranges. Over eons, these volcanic piles were blanketed by sediments, layers of silt and chemical precipitates settling into the abyssal plains. Then, in a colossal act of planetary compression, these entire submarine worlds were caught in a tectonic vice. They were crumpled, folded, and thrust upwards, scraped off the descending oceanic plate, and welded permanently onto the unyielding edges of the growing Cratons. The intense pressure and heat metamorphosed the original black basalt into a distinctive greenish hue, giving these belts their name. The presence of perfect pillow lava structures within these belts is our definitive proof that they formed deep underwater, a snapshot of an ancient seafloor frozen in stone. The chemistry of the volcanic rocks within Greenstone belts tells a story of a planet with a much more violent metabolism. They point to magma sources and eruption rates far more intense than anything seen in the modern world, suggesting that the early Earth's tectonic breathing was not the steady rhythm we see today, but a series of deep, convulsive gasps. These fossilized oceanic remnants are the tangible evidence of a world building its continents in fits and starts, adding new land at the margins with every powerful exhalation from the mantle below. Sometimes the planet's steady breath became a fiery cough. While the Supercontinent Cycle describes a deep, rhythmic pulse, Earth's history is also scarred by moments of sudden, violent release, geological events so immense they can only be described as planetary adrenaline shots. These are large igneous provinces, or LIPs for short. Imagine not the slow, creeping spread of a mid-ocean ridge, but a catastrophic rupture in the planet's skin, a wound through which millions of cubic kilometers of molten rock flood onto the surface in a geological instant. These events are the work of mantle plumes, but not the ordinary, steady upwellings that drive regular convection. These are superplumes, colossal pillars of superheated rock that detach from the very edge of the Earth's core and surge upwards through the mantle like a thermal torpedo. When one of these plumes reaches the lithosphere, it does not just nudge it, it utterly overwhelms it. The crust bulges, fractures, and splits open along vast fissures, not a single volcano but a continent-sized line of fire. For hundreds of thousands of years, lava erupts in relentless, flood-like waves, burying entire landscapes under layer upon layer of basalt, building plateaus of solid rock that can be miles thick and cover areas larger than modern countries. The Deccan Traps in west-central India are the eroded remains of one such event. The sheer volume of lava erupted there is almost incomprehensible, enough to bury the entire contiguous United States under several meters of rock. An even more massive event created the Ontong Java Plateau, a submerged LIP in the Pacific Ocean whose volume is so vast it dwarfs every mountain range on the planet combined. The immediate geological impact is staggering, but the true planetary shock comes from the gases. These colossal volcanic outpourings release unimaginable quantities of carbon dioxide and sulfur dioxide directly into the atmosphere. The effect is a brutal whipsaw for the global climate. First, sulfur aerosols can blot out the sun, triggering a volcanic winter that may last for decades. Then, the long-lasting CO2 takes over, unleashing a runaway greenhouse effect that bakes the planet. The oceans acidify, oxygen levels plummet, and the chemical balance of the entire world is thrown into chaos. It is no coincidence that the formation of several large igneous provinces aligns perfectly with the most severe mass extinctions in Earth's history, including the event that ended the age of the dinosaurs. In these moments, the planet's internal engine did not just breathe, it roared. The steady drift of continents could be violently accelerated, rift zones forced open, and the very pace of tectonic change set into a frantic, feverish race. The planet's fiery breath can sometimes bring an unthinkable chill. This profound paradox lies at the heart of the Snowball Earth hypothesis, a theory that links the rhythmic dance of continents directly to a world entombed in ice. During the deep past, on at least 2 occasions, our entire planet may have transformed into a single, glittering sphere of white. From pole to pole, oceans froze into a solid lid of ice perhaps a kilometer thick, while land masses lay buried under glacial sheets that reflected the sun's heat back into space. The trigger for this global deep freeze was not a distant supernova or a sudden dimming of the sun, but the planet's own tectonic breathing. When a supercontinent like Rodinia assembled, it often clustered its landmasses near the warm, moist equator. This tropical positioning was crucial. In a hot, wet climate, the chemical weathering of silicate rocks accelerates dramatically. Rain, which is naturally slightly acidic, reacts with the fresh rock exposed by the growing mountains of the new supercontinent. This chemical reaction pulls carbon dioxide, the primary greenhouse gas, out of the atmosphere, locking it away in carbonate minerals that are eventually washed into the ocean. Normally, volcanic outgassing from the planet's interior replenishes this lost CO2, maintaining a stable climate. But the supercontinent itself acted as a colossal lid, suppressing widespread volcanic activity. With the planet's CO2 intake valve wide open and its replenishment system stifled, atmospheric carbon dioxide levels plummeted. The greenhouse effect weakened, and global temperatures began a precipitous fall. Once a certain threshold was crossed, the runaway ice albedo effect took over. White ice and snow reflect sunlight, which cools the planet further, which creates more ice, which reflects even more sunlight. In a geological blink, this positive feedback loop could have encased the entire world in ice, a chilling direct consequence of the continental inhalation. The evidence for this incredible scenario is written in the rocks. Geologists find ancient glacial deposits, called tillites, in places that were at the equator at the time. They discover layers of carbonate rock sitting directly on top of these glacial layers, a chemical signature of a sudden, extreme greenhouse recovery. How could life possibly survive a global icebox, and what force was powerful enough to finally break the planet free from its icy prison? The planet's great ice ages were not eternal prisons. The same volcanic forces that could trigger extinctions also provided the escape route. While the white globe reflected sunlight, its volcanic heartbeat continued beneath the frozen shell. For millions of years, carbon dioxide from undersea volcanoes built up in the ocean and atmosphere with no weather system to scrub it out. Eventually, the greenhouse gas concentration reached a critical tipping point, so potent that it overwhelmed the ice albedo effect. The thaw, when it came, was likely geologically rapid, a dramatic meltdown that transformed the planet from an icebox into a hothouse. This violent climatic whiplash, from deep freeze to sweltering heat, subjected the simple life forms of the time to an evolutionary trial by ice and fire. The very rhythm of the continents, their assembly triggering the freeze and their breakup allowing the volcanic recovery, had created the ultimate pressure cooker. This profound instability was not a one-time catastrophe but a recurring theme in the planet's story, a direct consequence of its dynamic nature. A stable, tectonically quiet planet might have nurtured a gentle, simple biosphere for eons. But our world's restless geological heart ensured that its environment was in constant flux, and life was forced to keep pace. The breathing of the continents did not just change the scenery, it turned the entire planet into a crucible for biological innovation. Each time the supercontinent cycle reshuffled the world's geography, it rewrote the rules for every living thing. The collision of continents threw up vast mountain ranges, not just as barriers but as engines of change. As these new mountains rose, their fresh, unweathered rock was exposed to wind and rain. Erosion rates skyrocketed, and torrents of mineral-rich sediment poured into the oceans. This was not mere dirt, it was a nutrient slurry, a fertilizer flood that could fundamentally alter the chemistry of the seas. Many scientists point to this exact process as a potential trigger for the Cambrian explosion, that remarkable moment in evolutionary history when life suddenly diversified into a wild menagerie of complex forms. The shallow, sun-drenched continental shelves, another product of tectonic rearrangement, became the perfect nurseries for this new biological experimentation. At the same time, the opening and closing of seaways acted as evolutionary switches. A newly formed ocean passage like the Isthmus of Panama could connect previously isolated ecosystems, sparking fierce competition. Conversely, a rising mountain chain or a receding sea could split a single population in two, isolating groups and allowing them to evolve in completely different directions, a process that ultimately created entirely new species. This constant tectonic reshuffling forced life to adapt, migrate, or face oblivion. The incredible diversity of life on Earth is not just a product of random genetic mutation. It is a direct response to the stage being constantly rebuilt by the planet's own internal dynamism. The vitality of the continents, their slow and rhythmic breath, was a primary driver of biological richness. This deep connection forces a profound question. If the liveliness of the planet was essential for our own existence, where did that initial spark of geological life itself come from? Even the air we breathe is a gift from the planet's deep geological pulse, one of the most dramatic turning points in Earth's history. A moment that forever altered life's destiny was the Great Oxidation event. Around 2.4 billion years ago, the atmosphere, which had been a suffocating blend of methane and carbon dioxide, began to fill with a strange, toxic, and reactive new gas, oxygen. This was not a random act of chemistry. It was a direct consequence of the living continents at work. The story begins with a new kind of life, cyanobacteria, which had mastered the art of photosynthesis. They used sunlight to produce energy, and as a waste product, they released oxygen. For millions of years, this oxygen never accumulated. It was immediately mopped up by the environment, reacting with dissolved iron in the oceans and with volcanic gases. The tectonic trigger came from the constant churning and reshaping of the continents. As mountains rose and eroded, they dumped immense quantities of sediment into the shallow seas that fringed the newly formed continental shelves. These quiet, underwater plains became the perfect graveyards for dead microbial life. The bodies of countless cyanobacteria and other organic matter would settle into the mud, and this thick, blanketing sediment acted like a geological seal, burying the organic carbon before it could be consumed by oxygen-breathing decay processes. For every atom of carbon buried this way, a molecule of oxygen was left behind in the water and air, freed from its chemical bonds and allowed to accumulate. The proof of this planetary transformation is locked in the rocks themselves, in stunning formations known as banded iron formations. These are beautiful, striped layers of red and gray rock that represent a global chemical crisis. As oxygen built up in the oceans, it reacted with the dissolved iron that had saturated the ancient seas, causing the iron to rust on a planetary scale. This rust settled to the seafloor in rhythmic, alternating layers with silica-rich chert, creating a permanent record of the ocean slowly choking on this new, reactive gas. This was not a peaceful transition. It was a toxic catastrophe for the ancient, oxygen-hating life forms that dominated the planet, leading to what was likely the first mass extinction in Earth's history. Yet from this tectonic and biochemical upheaval, a new world was forged. The planet's mechanical breath, its cycle of mountain building and sediment burial, had directly enabled a revolution in the air. This profound link reveals that the geological and biological spheres are not separate kingdoms, but have been intertwined partners from the very beginning, with the very rhythm of the continents dictating the air that life would one day depend upon. This elegant vision of a breathing planet is not the only story written in the stones. The idea of a rhythmic, biological-like cadence to continental motion faces profound challenges from other, equally compelling models of our early world. One of the most prominent alternatives is the stagnant lid hypothesis. In this view, the infant Earth was not a mosaic of shifting plates but a single, continuous shell of rock, a rigid, unbroken lid sealing the churning mantle beneath. Without the global network of subduction zones and mid-ocean ridges we see today, the planet's internal heat would have escaped not through the lateral drift of plates, but primarily through vertical processes. Imagine a pot of soup with a thick, solid skin on top. The heat from below could only escape by building up until it finally burst through in colossal, stationary supervolcanoes. This model suggests a world without continental drift in its early chapters, a planet where the familiar tectonic breathing had not yet begun. Other scientists propose a hybrid scenario, the episodic lid model. This theory paints a picture of a world that alternated between long, quiet periods of stagnant lid conditions and brief, catastrophic bursts of global tectonic activity. In this stop-start world, heat would accumulate beneath the rigid shell for hundreds of millions of years until the pressure became unbearable. The entire lid would then fracture and founder in a planet-wide tectonic surge, a geological revolution that would rapidly reorganize the entire surface before the lid resealed and the cycle of buildup began again. Experts like geodynamicist John Cornoga argue that the hotter, softer mantle of the early Earth would have behaved differently, potentially resisting the organized, large-scale convection that drives the modern plate tectonic system. The debate hinges on the interpretation of an incredibly sparse and mangled rock record. How do you read the first pages of a book when 99% of them have been burned away? The evidence is not clear-cut, and the same ancient zircon crystals or greenstone belts can be interpreted in multiple ways, their silent testimony open to conflicting translations. This vibrant scientific controversy is not a sign of weakness, but a testament to the dynamic process of discovery. It reveals that our understanding of Earth's youth is still a living, breathing thing itself, evolving with every new clue pulled from the deep time archives. Iceland is the Earth's living anatomy lesson. It is one of the few places on the planet where you can stand with one foot on the North American tectonic plate and the other on the Eurasian plate, feeling the monumental forces of separation in the very ground beneath you. This island nation is not just crossed by the Mid-Atlantic Ridge, it is the Mid-Atlantic Ridge, forced above the waves by a colossal upwelling of heat from deep within the mantle. This rare combination of a divergent plate boundary and an underlying mantle plume creates a hyperactive volcanic nursery, a place where new crust is being forged at a rate far exceeding the norm. Here, the planet's exhalation is not a slow, theoretical process. It is a visible, audible, and palpable reality. Fissures tear open the Earth, steam hisses from countless vents, and lava regularly pours forth to add new land to the island's edges. This is our clearest modern window into the Archean Eon, a time billions of years ago when the entire planet may have looked more like Iceland, its crust thinner and its volcanic metabolism dramatically more vigorous. The pervasive volcanism and rapid crustal formation we witness here offer a scaled-down, observable model of the kind of rampant geological activity that would have characterized the planet's great outward breaths, those periods of continental dispersal when new ocean floors were born in a frenzy. In Iceland, the theoretical breathing Earth becomes an immediate sensory experience, a place where you can watch the planet literally rip itself apart and rebuild in real time. This living laboratory shows us that the forces which once sculpted the entire globe are not extinct. They are merely concentrated, allowing us to witness the same primordial engine that scattered the ancient supercontinents still quietly humming away, constantly reshaping our world. These theoretical debates find their proving ground not in the field, but inside the humming silence of a supercomputer. To test whether a breathing Earth is more than a beautiful metaphor, scientists build digital planets from the ground up. This is the realm of geodynamic modeling, a discipline where the impossibly slow dance of continents is accelerated into a breathtaking visual symphony. Researchers begin by defining the fundamental rules of their virtual world, inputting complex equations that govern the behavior of rock under immense heat and pressure. They set parameters for the mantle's viscosity, a measure of its resistance to flow, and define the density of different rock types. They simulate the relentless heat flowing from the core and the cooling effect of space on the surface. With these physical laws in place, they press start and the simulation begins. A swirling, chaotic mass of color representing the mantle slowly self-organizes. Over millions of simulated years, you can watch plumes of hot rock rise from the depths, spread beneath the lithosphere, and cool into sinking sheets. You can see continents represented as buoyant blocks being tugged and pushed by these subterranean currents. The true test comes when these models, running for days or weeks of real time, begin to produce the very patterns we dig out of the rock record. Can the simulation on its own generate the rhythmic assembly and breakup of a supercontinent? Can it recreate the frantic sprint of India or the stable endurance of a Craton? When a digital planet starts to breathe with the same cadence as our own, it provides a powerful validation of the underlying theory. These models become digital time machines, allowing for profound what-if experiments. What if the early Earth's mantle was just a little bit hotter? The simulation might show a world of episodic, catastrophic surges instead of a steady rhythm. What if a massive mantle plume struck a supercontinent at a different angle? The model could reveal an entirely different arrangement of modern continents. This fusion of geology and computer science gives us a unique laboratory, one where we can witness the entire 4.5 billion-year biography of our planet play out in a matter of days, offering insights into Earth's dynamic heart that are simply impossible to gain from a hammer and a rock alone. Earth's geological vitality may not be a solitary wonder but a universal key to life. As we discover thousands of exoplanets orbiting distant stars, the theory of living continents transforms our search for habitable worlds. We are no longer just looking for planets in the so-called Goldilocks zone, where temperatures are just right for liquid water. We are now searching for worlds that breathe. A planet with a stable, long-term climate capable of nurturing life almost certainly requires a geological thermostat, and plate tectonics provides exactly that. This process, the carbon silicate cycle, is a planetary feedback loop of breathtaking elegance. Volcanoes constantly exhale carbon dioxide into the atmosphere, which traps heat and warms the planet. This warmth drives rainfall and weathering, which breaks down silicate rocks on the surface. The chemical reaction pulls CO2 out of the air, forming carbonate minerals that are washed into the oceans. These carbonates are then drawn down into the mantle at subduction zones, where they are eventually recycled and released again by volcanoes millions of years later. On a world without this cycle, like Mars or Venus, the climate system eventually runs to a disastrous extreme, either freezing solid or boiling away. A tectonically active planet, however, possesses a built-in climate control. If the world gets too warm, weathering increases, pulling down more CO2 and cooling it off. If it gets too cold, weathering slows, allowing volcanic CO2 to build up and warm the planet again. This self-regulating pulse is what gives a world the long-term stability life needs to evolve and thrive. The search for these living worlds, however, presents an immense challenge. How can we possibly detect the slow drift of continents or the grinding of plates across light years of emptiness? We cannot see their surfaces, but we may soon be able to read their atmospheres. Scientists are developing methods to analyze the chemical composition of an exoplanet's air, looking for specific cocktails of gases that betray an active geology. The simultaneous presence of certain sulfur compounds and methane, for instance, could point to active volcanism replenishing the atmosphere, a strong hint of an internal geological engine. The discovery of such a world would be a monumental moment, suggesting that the dynamic restlessness of our own planet is not a fluke but a fundamental ingredient in the recipe for a living universe. Our world's deep, rhythmic breath may be the very signature we are searching for in the cosmos, a beacon pointing toward another cradle of life. Our own species has now become a geological force. We are living in an age defined by human activity, a period many scientists call the Anthropocene, where our collective actions ripple through the Earth systems with the power of a continent. This is not a metaphor. The sheer mass of material we move each year through mining, construction, and agriculture dwarfs the natural sediment transport of all the world's rivers combined. We are now the primary agents of erosion on the planet's surface, reshaping landscapes at a rate that rivals the titanic forces of ice and water. Our industrial metabolism burns through fossil fuels that were buried over hundreds of millions of years, releasing carbon dioxide into the atmosphere in a geological instant. This human-driven pulse of carbon is currently over 100 times greater than the natural background flux from all the world's volcanoes. We are flooding the planetary system with a greenhouse gas that its geological thermostat, the carbon silicate cycle, was designed to manage over millennia, not decades. This is the profound paradox of our time. We are the first life forms to truly understand the planet's deep, rhythmic breath, yet our actions now threaten to throw that rhythm into a dangerous, unpredictable spasm. We cannot stop the tectonic plates from their slow dance, but we are drastically altering the surface conditions that their movements have so carefully regulated for billions of years. The same global climate stability that allowed human civilization to flourish is a direct product of that long-term geological balance. By disrupting it, we are effectively tampering with the fundamental life support system of our world. This realization imposes a staggering responsibility. As the conscious inhabitants of a living planet, do we have a duty to align our own short-term rhythms with its deep, enduring pulse? The story of the breathing Earth now has a new and urgent chapter, one that we are writing ourselves with every choice we make. Long before the first geologist cracked open a rock, humanity listened to the Earth and heard a heartbeat. Cultures across the globe, separated by vast oceans, independently wove a common thread into their creation stories, the profound intuition that the world is a living, conscious entity. The ancient Greeks gave this idea a name, Gaia, the primordial goddess who was the earth itself, a being from whose body the mountains, seas, and sky were born. This was not merely a personification of nature, but a philosophical concept of a unified, self-regulating system, a vision that uncannily prefigures our modern understanding of a biosphere deeply intertwined with its geological foundation. On the other side of the world, numerous traditions speak of a world turtle, a colossal being that supports the land on its back. In some Hindu cosmologies, the turtle rests upon a serpent, representing the endless cycles of time, while in many indigenous American narratives, the turtle's shell is the very continent we inhabit. These are not literal descriptions, but powerful metaphors for stability and motion, for a world that is both a foundation and a participant in a grander cosmic dance. The turtle does not stand on a static pillar, it swims through the cosmic ocean. These myths capture the essence of a dynamic planet, one that moves and changes, supported by a deep, living force. Even the concept of a world tree, like Yggdrasil from Norse mythology, with its roots delving into unseen realms and its branches holding the heavens, mirrors the structure of our planet with its deep mantle roots and mountainous peaks. How is it that these separate cultures, with no means of communication, all arrived at this same fundamental perception of an animate Earth? It seems our ancestors, by simply observing the rhythms of earthquakes, volcanic births, and the slow wearing down of mountains, sensed a vitality that science is only now beginning to quantify with equations and seismic sensors. They felt the planet's breath in the wind and its pulse in the trembling ground. This is not to say that ancient myth is a blueprint for plate tectonic theory, but rather that the human experience of the world, when distilled through generations of profound observation, often points toward a deeper truth. Our oldest stories and our newest discoveries are converging on the same breathtaking realization that we do not live upon a dead rock, but are part of a vast, living being whose slow, majestic rhythms are the very tempo of life itself. The world map hanging on your wall is a fleeting snapshot in a multi-billion-year epic. The continents you recognize are still in motion, drifting on their slow, inevitable paths toward the next great gathering. Based on the current trajectories of the plates and the relentless pull of subduction zones, scientists can project the Earth's geography hundreds of millions of years into the future. The most prominent prediction is a supercontinent called Pangaea Proxima, a name that acknowledges it would be the next in a long lineage of colossal landmasses. One compelling model suggests the Atlantic Ocean, which is still widening today, will eventually slow its expansion. A new subduction zone will form off the eastern coast of the Americas, perhaps triggered by the dense, old floor of the Atlantic beginning to sink. Once this happens, the process will reverse. The Atlantic will start to close, like a zipper being pulled shut, dragging the Americas eastward on a collision course with a combined Europe and Africa. Imagine the entire Atlantic basin shrinking away, its seafloor consumed, until the coast of Brazil nestles against the curve of West Africa once more, and North America smashes into southern Europe. This collision would throw up a new Himalayan-scale mountain range along the entire suture, a colossal spine of rock marking the weld of a new world. Alternatively, a different model, often called Amasia, envisions the closure of the Arctic Ocean instead, with the Americas continuing their westward drift to collide with Asia, sealing off the Arctic and fusing North America to Siberia. The precise outcome depends on subtle gravitational nuances and the evolving dynamics of the mantle below, but the ultimate result is the same. In roughly 250 million years, the scattered continents of today will be reunited. This is not science fiction, it is the straightforward extrapolation of forces we can measure right now. The familiar outlines of our continents are temporary, destined to be crumpled together and lost, just as the outlines of ancient Pangaea were. This forward look is a powerful reminder that the planet's breath is a cycle without end. The ground beneath us may feel permanent, but it is merely a passenger on a journey whose final destination is another beginning. That same planetary breath that scattered continents also filled the Earth's treasure chests. The very metals, fuels, and minerals that power our modern world are not randomly scattered gifts, but the direct, logical consequence of the planet's tectonic rhythm. When continents collide in a great tectonic inhalation, they do more than just throw up mountain ranges, they act as colossal forges for metal. Deep beneath the growing mountains, vast chambers of magma slowly cool. As they solidify, they release hot, mineral-rich fluids that are forced upwards through a network of cracks in the overlying rock. These fluids concentrate metals like copper, molybdenum, and gold, depositing them in a distinctive type of formation known as a porphyry deposit. The Andes mountain chain, a product of the ongoing collision between the Nazca Plate and South America, is lined with these incredible metal factories, which provide nearly a third of the world's copper, the essential metal for all electrical wiring and renewable energy technology. The gold that fills vaults and the molybdenum that strengthens steel are often pulled from the very same geological events that built the landscapes we see. When the planet exhales and continents begin to pull apart, it creates a different kind of wealth. The stretching crust sags downward, forming massive sedimentary basins that can be hundreds of miles across. Over millions of years, these sunken areas fill with layers of sand, silt, and organic debris, the remains of ancient life. Buried deep and cooked by the Earth's internal heat, this organic material slowly transforms into the coal, oil, and natural gas that have fueled our industrial age. The North Sea, a vast hydrocarbon province, lies in a basin that formed as Europe began to rift away from North America. Even the ancient seafloor itself holds immense riches. At the divergent boundaries where new crust is born, superheated water circulates through the fractured rock, leaching out metals like zinc, lead, and silver from the surrounding crust. This metal-rich water erupts from hydrothermal vents on the dark ocean floor, creating towering chimneys that precipitate out massive sulfide deposits. While most of these are lost to the relentless cycle of subduction, some are scraped off and preserved on the edges of continents, becoming the fossilized vents we now mine on land. This deep connection means that every time we fill a gas tank or use a smartphone, we are utilizing resources created by the Earth's dynamic pulse. Understanding this rhythm is no longer just an academic pursuit. It is the key to finding the resources we need for the future, forcing us to read the planet's deep history as a map to its hidden treasures. Beneath the ocean floor, in total darkness and under crushing pressure, lies a second world of life. This is the deep biosphere, a realm where Earth's tectonic breath becomes a literal life force. We have long believed that all life depends on the sun, but here, in the cracks and pores of the crust, vast ecosystems thrive completely independent of sunlight. Their existence is made possible by the constant, slow circulation of water through the planet's rocky bones. Along the vast mountain chains of the mid-ocean ridges, where the planet exhales new seafloor, cold seawater is drawn down into the fractured crust. It percolates deep where it is heated by the magma-chambered heart of the ridge. This superheated water then reacts violently with the surrounding basalt rock in a process called serpentinization. The chemical reaction transforms the rock, but more importantly, it releases a bounty of energy-rich compounds, including hydrogen and methane. For most life, these would be useless, but for specialized microbes, they are a feast. These are chemosynthetic organisms, the true power players of the deep. Instead of using sunlight to make sugar, they use the chemical energy from hydrogen or methane to fuel their metabolism, building organic matter from the raw ingredients of rock and water. They are the primary producers in a food web that operates in perpetual night, a web that can include bizarre worms, blind shrimp, and other creatures, all ultimately nourished by the planet's internal heat. This discovery fundamentally rewrites the rules of biology. It proves that tectonic activity is not just a geological process, it is a biological necessity. The same forces that rip continents apart and build mountains are also pumping energy into a hidden, global ecosystem of staggering scale. Some scientists estimate the total mass of life in this deep biosphere may rival or even exceed all life on the surface. This transforms our understanding of a living planet. The continents may breathe, but the whole Earth metabolizes, its internal chemistry sustaining life from the inside out. This deep partnership between geology and biology raises a profound possibility. If a planet's own tectonic engine can power life in the dark, then worlds far from the warmth of their sun, like Jupiter's moon Europa or Saturn's Enceladus, could still be teeming with life in their subsurface oceans. Our search for life beyond Earth must now listen for the quiet metabolic hum of a world feeding itself. The greatest dying in our planet's history began with a whisper from its depths. 252 million years ago, at the close of the Permian period, the supercontinent Pangaea was fully assembled, a single, massive landmass that had drawn its breath deep and held it. Then, in a region that is now Siberia, the planet exhaled with a violence never seen before or since. The crust fractured not in a single volcano, but along a network of fissures hundreds of miles long, vomiting forth enough lava to bury the entire planet under 10 feet of rock. This was the Siberian Traps, a large igneous province of almost unimaginable scale. For nearly a million years, the eruptions continued relentlessly, but the lava itself was not the primary killer. It was the invisible gases. Trillions of tons of carbon dioxide were injected directly into the atmosphere, triggering a runaway greenhouse effect that sent global temperatures soaring. The oceans, absorbing this CO2, turned sharply acidic, dissolving the shells of marine creatures and collapsing the entire foundation of the food web. On land, the warming and acid rain stripped soils of nutrients, while the oxygen levels in the ocean plummeted, creating vast, suffocating dead zones where nothing could live. In less than 60,000 years, a geological blink of an eye, 96% of all marine species and 70% of terrestrial vertebrate species vanished forever. This was not a slow decline but a swift, systematic collapse of the global biosphere, a direct and brutal consequence of the planet's internal fury. The same tectonic forces that had painstakingly assembled the continents and created new environments for life to flourish had, in a single, violent outburst, nearly reset the clock of evolution to zero. The planet's breath, so often a source of stability and renewal, can also be a weapon of mass destruction. How does a world recover from such a profound biological annihilation? Our planet is never silent. Even in its moments of greatest apparent calm, the Earth emits a persistent, low-frequency drone, a sound far below the range of human hearing known as the seismic hum. This is not the violent shudder of an earthquake, but a gentle, continuous vibration that resonates through the entire globe, a modern and audible connection to the planet's dynamic interior. The primary source of this hum is the relentless energy of the ocean. Giant storm systems churn the seas, creating powerful waves that travel for thousands of miles. When these waves finally reach the shallows of a continental shelf, their energy is transferred downward, pounding the seafloor with a rhythmic force that sets the entire crust ringing like a massive, silent bell. This oceanic drumming is then amplified by the constant pressure changes in the atmosphere, a global push and pull on the planet's surface. Together, these forces create a symphony of subtle motion, a fundamental note in the key of our living world. For decades, this hum was merely a theoretical curiosity, lost in the noise of more dramatic seismic events. But today, with networks of incredibly sensitive seismometers spread across the globe, scientists have learned to isolate and listen to this sound. They use it not as a geological oddity, but as a powerful tool for vision. Just as a doctor uses a CT scan to see inside a human body without making a single incision, geophysicists use the Earth's hum to image the deep interior with stunning new clarity. The way this constant background vibration bends, speeds up, or slows down as it passes through different materials reveals the hidden architecture of our planet. It can map the edges of a sinking tectonic slab as it plunges into the mantle, trace the rising heat of a mantle plume from the core, and even detect the subtle boundaries of ancient cratonic roots. This ever-present vibration is the most tangible proof that our planet is a system in constant energetic flux. The ground you stand on is not a solid, motionless stage, but a surface rippling with the deep, resonant frequencies of a world that is truly, physically alive. Listening to its hum allows us to eavesdrop on the grand, slow-motion dance of the continents, hearing the faint but unmistakable sound of the Earth breathing. This understanding shatters the very idea of solid ground. We build our cities, draw our borders, and etch our histories onto a surface that is fundamentally transient. The theory of living continents does more than rewrite geology textbooks. It demands a complete reimagining of our place in the cosmos. For centuries, humanity has viewed the Earth as a stable platform, an unchanging stage upon which the drama of life unfolds. We called it terra firma, the firm land, a name that now feels like a profound misnomer. We are not standing on a finished product, but on a single frame in a movie billions of years long. The mountains we see as eternal are temporary wrinkles, the oceans between us are fleeting gaps, and the continents that define our world maps are merely the current configuration in an endless dance. This realization carries a deep existential weight. Our entire civilization, with all its triumphs and tragedies, is built upon a surface that is actively moving, breathing, and recycling itself. The ground we trust to hold our homes is part of a cycle of unimaginable violence and creativity, where entire mountain ranges are born and then ground to dust, and where oceans wider than any today have opened and closed. What does it mean for our legacy, for our monuments and nations, to know they are all destined to be geological fodder? This perspective cultivates a powerful humility. We are not the masters of a dead rock, but temporary guests on a vast, living entity with its own ancient, indifferent rhythms. Our lifespan is a flicker compared to a single tectonic breath. This is not a reason for despair, but for a profound shift in connection. It invites us to see ourselves not as separate from nature, but as a brief, conscious part of its grand, dynamic flow. This can become the foundation for a new environmental ethic, one rooted not in saving a static planet, but in aligning our short-term actions with its long-term vitality. Our responsibility is not to preserve a museum, but to honor the ongoing story of a living world. Our journey through the living continents leads to one inescapable truth: the ground beneath us is a vibrant participant in the story of life. This is not a world of inert rock and passive landscapes, but a single, interconnected system where the planet's deep, tectonic breath has orchestrated everything from the air we breathe to the very metals in our hands. That rhythmic pulse of assembly and breakup, the great inhalation and exhalation of supercontinents, has acted as a planetary metronome, setting the tempo for climatic revolutions and biological explosions. The catastrophic fury of a large igneous province is not a random disaster, but part of this same dynamic system, a reminder of the immense power simmering just below the surface. We are the beneficiaries of this ancient vitality, living on a world that has consistently rebuilt and renewed itself. Every mountain range, every ocean basin, and every mineral deposit tells a chapter in this epic. To understand this is to gain more than knowledge. It is to feel a profound connection to the incredible, living system we are privileged to call home. Let this perspective change the way you see every stone and every horizon. We would love to hear how this grand geological narrative has reshaped your view of our planet. Share your thoughts in the comments below and subscribe for more journeys into the deepest mysteries of our past.